Okay. I now also mention bit of miscellaneous things about different simulation approaches and kind of the reasons why then again we go towards Markov chain Monte Carlo, but and also kind of some of the computational issues behind these things. The direct simulation term used in book refers that we are directly able to sample from some specific distribution. Unlike then importance sampling, which first uses some proposal distribution, or Markov chain Monte Carlo, which uses iterative algorithm to sample from something else, but eventually produces something from the desired distribution. But in direct simulation, even that is kind of usually requiring that we are doing, for example, transformations. And we have kind of a lot of these algorithms that which can produce draws from these most popular distributions, some of which are then these analytic solutions for simplest models. And in some cases, we can then further extend by factorizing. For example, we had the example for normal inverse chi-squared joint posterior that we can factorize it to inverse chi-squared and normal, and then sample first from one and then from the other one, and so on. But then these are then restricted to limited set of models. Behind of all these simulations, it's good to realize also that computers are not generating usually real random numbers. It's pseudo-random number generators, which are deterministic, but they have such deterministic algorithm coming up with the next value that it's really difficult then to predict what that next value is unless you specifically know specific state of that generator, or you would have very, very long sequence, and then you would need to be able to search that specific sequence in very large number of states and so on. There are also bad pseudo-random number generators, but most of the software you are using good pseudo-random number generators, and also they are improving all the time. The benefit of then having these, that they are actually deterministic, is also that then we can set random seed and we can also actually repeat some computations exactly. But then it also means that it's important that we use different random seeds when we really want kind of more random looking behavior. I mentioned that some of these direct simulations are transformations. The classic way to get normally distributed so draws from normal distribution is Fox-Muller method, where we get two different uniformly distributed random numbers, and then we have these trigonometric transformations, and we get two independent draws from the normal distribution. And similar kind of transformations can be used to get many these common distributions. Some of them, the ways to do these are listed also in the end of PDA 3, and then there are many other books listing possible algorithms. For normal distribution, this is not the fastest. These trigonometric computations are actually so slow that there are many other alternatives which are faster. R uses just inverse CDF methods. So just knowing the CDF and finding what's the corresponding value for certain probability between 0 and 1. It's not the fastest possible method. There are faster existing, but it's still better than this Boxmuller. When we don't have these transformations, we could do then this grid sampling. So when you were using beta posterior, student T posterior, you had these functions which can use these transformations going from uniform to beta or student T. In BioAssau, we don't have, the posterior is not known form, and then that's grid sampling. But what if you would have more than 2 unknown parameters? So in case of 2 parameters, or if we just have 1 parameter, and if we are good at guessing, and maybe we can guess so well that the range where we put our grid is such that 1/3 has clearly non-zero density. In 2D, if the interesting density is here, now it's only 1/9 of the rows which are in the interesting region. This gets even more complicated at some point that here it also that if we look at this, that the bigger grid, only 1/9 were inside of where the density is non-zero. It's also that if we look at this kind of where the most of the rows here should be, that it's also that the kind of the we need to here have the draws also everywhere. Even this part has the highest density. These parts have lower density, but there are many of them. So we need many grid points also all over quite low density regions. If we would have 50 or 1,000 grid points per dimension, you can see that the number of grid points needed is quite large. And with this laptop and R and what is the normal distribution, normal density algorithm used to compute that, it's about 20 million grid function evaluations per second. And you can see that already with 10 parameters, having a fine grid and even 50 grid points per dimension is not that fine. These are infeasible times to compute. So, and most of the grid evaluations would be somewhere non-interesting, which are not contributing to the final expectation. The algorithms I saw soon are sometimes useful also in these higher dimensional cases, but then MCMC is specifically the one which generalizes easy to high dimensional cases and is able to kind of make the function evaluations where it matters and needs less function evaluations then. You have to remember that when I draw some density and then say that, oh, let's have a grid here, We can also imagine that I say that, okay, we hope between these two lines, the posterior somewhere, but you don't have any other information where, and then you just, you need to pay €1 per each function evaluation. You would really like as few function evaluations as possible to figure out where to evaluate to get quickly these expectations. Now instead of paying euros, you are paying just waiting time to get your posterior computations finished. In chapter 10, then there are three indirect, in chapter 10 we call the two indirect sampling approaches, rejection and importance, and then next week, MCMC. In rejection sampling, now the blue line is showing some arbitrary unknown distribution. I'm drawing now the line again in infinite many locations, but of course we are now evaluating it only in finite number of locations. We could in 1D do also these like this numerical inverse CDF or grid, but this rejection sampling also works sometimes in bit higher dimensions, or sometimes it's just much faster than these grid sampling approaches. We assume that we have some proposal here, the red dashed line, and we assume that this proposal is somewhat close to target distribution, and we assume that we have some direct simulation approach from drawing from this. Here the proposal is normal distribution, and we are using then algorithm drawing from normal distribution quickly. In addition, here we have then set such that there's this constant m, and we set so that m times this proposal distribution is now larger everywhere than this target distribution. We can then draw quickly from the proposal and then quickly decide whether we accept or reject this draw. And you could see that all these green and red ones, they are all from normal distribution, but we accept only those which in this graphical illustration are below the green line, and reject which are above green or blue. Maybe it's cyan. And we can do this rejection easily so that we know what is the m times the proposal density, and after we got this random draw, we evaluate the true target density at that location, and we get this proposal probability m times g divided by q. And we just then need one uniform random between 0 and 1 to decide whether we accept or reject. And now, when we reject those which are above this cyan line, then the rest of them are distributed according to target distribution. The difficulty with this approach is how we choose good proposal distribution. If because now we had the restriction that the proposal distribution has to be such that there's the multiplier which makes it everywhere higher, but then if it's badly chosen, we would reject often, and that we don't want that. There are not that many cases where there are very good proposal distributions. There are some, like MATLAB is using ziggurat methods and then doing in the tail part of these rejection sampling things. But this is very common situation that we have the proposal distribution is actually non-truncated distribution, and the target distribution is the truncated distribution. So here, for example, we draw from normal, and the target distribution happens to be truncated normal, and we just draw values away which are below some threshold. This is something that is variation of this is used also in one of the Bayes-Assau examples. We can say that the number of accepted draws is the effective sample size. Those accepted draws are independent, and then we can use the in the first part of the lecture told these Monte Carlo standard error estimates. With that proposal, the proposal is somewhere very much higher than the target, and we are rejecting a lot, and we get low effective sample size compared to all the draws from the proposal. And especially when the number of dimensions increase, selection of good proposal gets very difficult. Impedance sampling makes this partially easier, and specific reason why this is in this course now emphasized a bit more is that it's very useful now in leave and out impedance sampling, where we are already sampled from the full data posterior distribution, and our target is posterior distribution given that we remove one of the observations from likelihood. And these are usually very similar. Here again, using the same kind of the arbitrary the target distribution, normal distribution proposal. Now we don't require that the proposal needs to be everywhere higher. And we can make a correction in both directions. Make a correction if the target is actually lower or if the target is higher than the proposal. And we can do it so that the first one is that we just obtained these draws from the proposal, which is in this case normal distribution. But when we compute some expectation, we are weighting these draws by ratio between the proposal and the target. So target divided by the proposal density is a weight. And the empirical the estimate for the expectation, you can see that there's the usual sum of some function values with the argument theta, which were these from the normal distribution. They are weighted, and then there's the self-normalization of the weights under the line. And you can see then that there's a higher weight if the target distribution is higher than the proposal, and there's a smaller weight if the target distribution is lower than the proposal. And we don't need to have these normalized. That's why there's the self-normalization also going. And this shows now the blue line is then this kind of how we would weight each draw, and the red lines are then again these normally distributed and what would be the weight for each of those draws. And we need here we are weighting a bit more those draws which were near tails and less which were in the middle. As you could see, In the middle, the proposal was higher, and in the tails, it was lower. And that can be corrected with weights. It's also possible to importance resampling, so that we can then resample from those, like here, the normally distributed ones, based on these importance weights, which helps that then we kind of get draws which have uniform weights. I have an illustration for this. The problem with this importance sampling, importance weighting, is that if the proposal distribution is not good, we have high variation of these importance weights. If some of the importance weights are really big and rest really small, it's not effective in a way the one is dominating too much. We would like to have low variance, and we also know that in the kind of the worst case, we have situations where the proposal distribution tail goes down too fast. There's still some density for the target, and we actually end up in a case that we get sometimes really very big weights, and if it's really rarely, we get this kind of case where the variance of these importance weights is actually infinite, and then this fails. I show some examples of the kind of another example of the kind of the variation of the weights, and when you are doing the exercise, you can use ready-made functions to check importance sampling, and I will also later then talk more about these checking of this importance sampling. But you don't need, for making the exercise, you don't need all the details which are available in this paper. This is the biasa example, familiar for you, and the first we have evaluated the density in a grid. We normalize the grid cell to get grid cell probabilities, and we can then sample according to these grid cell probabilities, and we can then use these samples, the posterior draws, to compute derived quantity, the LD50, and draw a histogram for that, and so on. One possible proposal distribution, and this was common thing to do in 1980s. It's now back in popularity, but more in variational inference case, but also a bit of this modal normal approximation. So we find the posterior mode, and just looking at the mode, we look at the curvature there and fit normal distribution there, which has the same curvature at the mode. You can see that it's somewhat similar. The normal distribution is missing that the true distribution is actually skewed longer in certain direction. We can get also directly from this normal distribution, we can draw a sample from that, just from multivariate normal. Here I limited it, so when computing the LD50, I limited it so that it's only for beta larger than 0. So assuming that, because you can see if you look at this normal approximation density and draws from there, some of the draws are for beta less than 0, saying that this chemical is actually beneficial, that there are less rats dying with higher dosages, but we know that it should be hazardous, so we can truncate, so using in that way rejection sampling, truncating this normal distribution, and we can then compute the LD50, and we can see that there's a similar shape, but it has longer tails. And we can check that standard deviation for LD50 from grid approach is 0.1, but now with the normal approximation, it has too much mass for small betas, and since LD50 is computed by minus alpha divided by beta, dividing with too many small values gets us much bigger standard deviation. So normal approximation is not so good here, but we can correct this using the impedance weighting or impedance sampling and impedance resampling. So we can now compute weight for each of the draw from the normal distribution, and according to these weights we can also do the resampling, so that then it's easier to compute these LD50s and plot this histogram, and we can also check that, okay, now standard deviation for LD50 is the same, very close, the same as from the grid approximation. So impedance sampling was able to correct this one. In this case, since we had only 2 dimensions, we could have managed just with the grid, but this normal approximation has been used, for example, in these 10 and 20 dimensional cases, and sometimes even 100 and 1000 dimensionals, and it can also work even in these very high dimensions, but it was popular especially in the moderate dimensions in 1980s. And again, the main reason is now that you have a familiar bioassay example to look at how impedance weighting and impedance resampling work, so that it's easier then when we go to leave out impedance sampling. One of the things about this impedance resampling is that that now you can see in the impedance resampling I've added a bit of jitter, and you can see some of the points are actually cluster of points. So those draws from the normal had large weight, and then when we did the impedance resampling, we got the from the same location many draws. It means that then this is kind of the downside of this approach, that actually these draws are not completely independent because they are coming from the same location many times. We could improve it by getting more draws from that normal distribution and so on, or improving the proposal distribution, but in this case it was enough. The correction was sufficient to get, for example, the uncertainty about LD50 with good enough accuracy compared to more like the grid approach. So this is showing even with the bigger those, you can see the clustering of points, which happens especially in the kind of that long tail, which normal approximation was kind of underestimating. And when we compare to grid, we can see that from the grid sampling we got more draws further away in the tail, but this weighting was enough for LD50. From this clustering of the points in importance resampling, we can also see the kind of that, okay, some of the weights were large, and we can look at also these importance sampling weights as is. It's a bit difficult to see that there's the largest weight is almost 0.04. The second largest is about 0.02. Then third largest 0.015. But they are there. So these, it means that now these draws were weighted much more. Is this problematic? We can diagnose that. Here would be, what if we would have perfect proposal distribution? So if we would be drawing from the actual target distribution, then the importance weights would be just 1 per S, 1 per how many draws we have. So we see that some of the draws have a smaller weight and some of them have larger. But actually there are anyway quite many around there. So maybe even if we have some larger weights, this is still fine. This is another way to look at it. If we rank these weights from largest to smallest and start to sum these weights, we can see that few of the first ones get a lot of actually quickly the cumulative weight. But it's not that bad in a way that there are many weights which are contributing before we reach cumulative weight of 1. And only quite small number of weights are not anymore accumulating this cumulative weight. It's possible to compute effective sample size. And this effective sample size starts that we have first normalized weights. So we have, because when we have the proposal density and target density, if the target density is unnormalized, we first normalize the weight. So here W tilde is the normalized weight. Just surf normalizing, so each weight is divided by sum of the weights. And then we have an equation, this 1 per square of sum of the weights. You can think now that if one of the weights is not one of the normalized weights is 1 and all others are 0, so 1 is dominating, then we would have in that sum, we would have just 1 and effective sample size would be 1. So if one weight is dominating, this correctly computes that effective sample size is 1. If all the weights would be equal, 1 per S, we would have there 1 per S squared, and then we would have S of those, so we would have S per S squared, and because it's under 1 per that, we get actually effective sample size of S. So we can also show that if we have equal weights, the effective sample size is the total number of draws. And then with something that not 1 dominating and not equal weights, we are somewhere between there. So we have a way to estimate also how good our proposal distribution is, and when thinking about what is our Monte Carlo error, we can use this effective sample size for importance sampling to check how many draws we need for certain accuracy. There's a first and second printing of PDA3 have error. Not certain which version is the online version, and overall, if you think there are other errors, you can see the errata at that address. So in this case, the effective sample size is 270, which is decent. Important thing now to recognize is that this effective sample size estimate has been derived from variance of W tilde. So it assumes that this variance is finite, and it's possible that it's non-finite. The paper cited has more about this Pareto K diagnostic, and I'll come also back to more about the Pareto K diagnostic later. But the idea is that we can look at the kind of the how these largest weights, how the tail of this weight distribution behaves, and if that tail seems to be very long, it's likely that that variance would be infinite, and then the effective sample size estimate is not valid. It actually happens that even if that would be infinite, we still get useful estimates. So that if the Pareto K diagnostic is just that we fit generalized Pareto distribution to the tail of this weight distribution, and that measures kind of the tail thickness, and then tail thickness is this K parameter, and then that K parameter tells us about reliability. In this case, we are on the edge case, so it's kind of that, yes, it would be better to have a better proposal distribution, and we are just about the kind of on the edge that whether we get useful estimates or not. And this Pareto K, so looking at the kind of the how thick tail the weight distribution has, it estimates the number of existing moments. And mean is a moment, variance is a moment, and we want to know whether variance exists. We have a very good situation if the K is below half, finite variance, central limit theorem holds, we get fast convergence, we get high effective sample sizes. If the K is larger than half but below 1, and actually in the important sampling it is kind of by construction, it's still generalized central limit theorem holds, so these expectations are valid. And because we are using also then Pareto smoothed approach to actually improve the weights, we get also decent effective sample size estimates as long as K is below 0.7. And there's more about in that paper. You don't need to read that paper for this course, but when making your exercises and project, you need to know this 0.7 value. So in your exercise, you repeat this kind of the similar thing what I had in the slides with the Bayes-Assau, just using different proposal distribution, and then you will evaluate also the effective sample size, and you can check the K value that your proposal is good. It's quite easy in this case because it's just two-dimensional case. And then later in the course, we use this important sampling for leave-and-out cross-validation. So in chapter 6, we come to model assessment, model checking how do you know whether your model is actually good description of the data, or comparing different models, which model is able to describe the data the best. But since we've already used the data to update the posterior distribution, we like to look at how good predictions our model can make for unseen data, and one way to do is this, that we fit the posterior with all except one observation and then try to predict the left out observation. But we don't want to do the full simulation for the full data and not for all possible leave and out data sets. But since this full data posterior is often very close to data where we remove just one observation, we can use this importance sampling many times very quickly and get this importance sampling leave and out cross validation. And then using this Pareto decay diagnostic, then can then tell when it's working well, and the Pareto smoothed part is also then improving the accuracy of these estimates. Running out of time, I'll talk about curse of dimensionality more next time, when I'll also then talk about Markov chain Monte Carlo. The benefit is that they go where most of the posterior mass is. When we go to higher dimensions, it's better to say where the typical set is. So they're doing the function evaluations where it matters. Certain MCMC methods, like what is used in STAN, especially scale well to high dimensions. The downside is that there's some additional things we need to take into account, but since in some cases these are the only hope we have, we just have to also then take care of the dependency and how to check that it's actually sampling from the desired distribution. In this course, there's briefly about Gibbs sampling. You will implement the simplest possible Metropolis algorithm so that you can see the connection again with the log density and how to generate draws. You don't need to implement this dynamic Hamiltonian Monte Carlo, but there's discussion about that, and then you use it via STAN, but it helps that you've seen the log density MCMC connection with Metropolis also when you are using this more advanced dynamic HMC. Okay, that's it for this time.